Hello, so I'm Carolyn Brighouse. I'm here to talk to you about some of my research. I'm in the philosophy department and the cognitive science department, and I'm also associate dean for student academic affairs. And I hope at this point in the summer you're beginning to feel that you're ready for your research presentation. I'm sure that comes with a lot of stress, but it will be wonderful for you to have done your work this summer and to present your work at the conference. I'm going to talk to you about some of my work, and this is an example of a question that I've been interested in for about 30 years, and somehow, even though I try and leave it behind, I get sucked back into it. So I just published a paper on it a couple of years ago, and so I'm going to talk a little bit about how that work's evolved over the last 30 years. I haven't worked on it all the time during that 30 years. I do come back to it from time to time, and I'll explain why. So I'm going to talk to you about understanding indeterminism, and the title of my talk is Identical Twins, Gummy Bears, that's the subtitle, and General Relativity. The gummy bears won't make a huge entry into the talk, but they're there. They are my favorite American candy anyway. All right, so I just want to say a little bit about what interests me. I'm interested in what the kinds of questions that fascinate me are the ones that lie at the foundations of math and physics and philosophy, right? So intersections of philosophy and mathematics, intersections of philosophy and physics. I have a training, undergraduate training in math and philosophy and a little bit in physics, and then my grad training is mostly in philosophy, but I have an amateur interest in mathematics, so I do work on, I continue to take grad classes in math even now, and I do work on sort of technical problems in philosophy of physics. I know that probably doesn't appeal to everybody who's watching this, but if you're interested in this stuff, or if you too find the philosophical foundations of math and physics interesting, I'd welcome a conversation. I'm always very happy to talk about these things. I love talking about them and thinking about them. Okay, so the question, the problem that I started working on a very long time ago, almost 30 years ago now, it is more than 30 years, is this problem that was described in a paper that was published in 1987 called What Price Spacetime Substantivalism, the whole story. And it's published by John Earman and John Norton, two philosophers of physics who were at the University of Pittsburgh at the time. And what they argue in that paper, actually building on the work of Einstein, a problem that Einstein was concerned about when he was trying to figure out how to formulate general relativity. They argue that this problem that Einstein was worried about I'll explain later what that problem was, is a reason to believe that general relativity is indeterministic. Okay, so the most natural interpretation of GR is that it's an indeterministic theory. The world, according to GR, is indeterministic, which is a radical conclusion. If you ever talk to a physicist and you say, I just heard in a philosophy talk that GR is indeterministic, they'll say, that seems wrong. Physicists will look at you askance. Quantum mechanics is indeterministic, and regretfully so, but certainly general relativity is not an indeterministic theory. So it's a controversial conclusion, and it was sort of published before I got to grad school, but right around the time where I was beginning to think about what I wanted to do, what kinds of work I wanted to do as part of my PhD, and I wanted to figure out what the right thing to say in response to this paper was. And I published my first paper on the topic in 1994, and it was controversial because I'll explain a little bit later why it was so controversial, but I basically said there's a very good way to avoid this conclusion that general relativity is indeterministic. And it was influential, which is great. You want your work to be influential. What's unfortunate is that its influence, I think, failed to capture something that I did highlight in the paper, which was that it wasn't quite right. There's a problem. in the view that I was trying to defend. Not one that I think is insurmountable, but actually one that I still don't really know how to solve. And I keep, actually in my work on this, or when I go to conferences, I keep trying to get people to focus on this problem so that they can, with a good conscience, defend this view that general relativity is not indeterministic. So, okay, first let's talk a little bit about determinism and indeterminism. Right, so I have here that they are modal notions. They have to do with possibility, necessity, right? Those are modal notions. And the intuitive idea is that a world is deterministic if there is only one physically possible future compatible with our past. This is taken from this particular characterization is one I like. It's simple, and it comes from a paper by Gordon Bullock from 1995. And the idea then is that if a theory tells you that the state of the world at a time is going to evolve in just one way, could only evolve in one way, then that theory is deterministic. If the theory tells you that given the state of the world at a time, there are several possibilities for how it might evolve in the future, then that world is, or the world according to that theory is indeterministic. Right, so the basic idea of indeterminism is that there's at least two possibilities for the future given the state of the world at a given time. Determinism is that there's a unique future. Right, now the challenge that is going to be sort of unveiled is, it's all well and good to have this be your characterization of determinism, but you better know you better know how to read your theory. You better know when is it that your theory tells you that there's more than one possible future, and when is it that your theory tells you that there's just one. And it's not always easy to figure out what the answer to that question is. And what I'm hoping to show you is that it's particularly difficult to unravel this problem and figure out exactly how to characterize determinism and indeterminism for a theory. Okay, so quantum mechanics is an example. I'm going to give you one example here of radioactive decay, which exhibits the indeterminism of quantum mechanics. So radioactive decay and half-life, and I'm sure that you all know this. I think I'm sure you've all taken chemistry or physics classes in which you've talked about this. Given a sample of some radioactive element, the half-life is the time at which half that sample will remain, right? So, and the indeterminism in quantum mechanics is sort of illustrated by which particular atoms in that sample will decay is undetermined, but the chance of any particular atom decaying is 0.5, and so as a result, after that time, half the sample will remain. So here's a very low-tech picture, right? If you take the world W at T0, there are many ways that world could evolve through time, right? Here we have 12 blue dots that are representing atoms of a radioactive substance, and after the half-life time, right, which let's say is T1, it could be that what remains undecayed are the top 4 and 2 of the bottom, or it could be that what remains undecayed are the bottom 4 and 2 of the top, and everything else has decayed. This should be W prime T1, not W T1 prime. So there are 2 different futures depending on which particular atoms decay, right? And in quantum mechanics, we've sort of learned to live with this. It was thought that perhaps if we just knew more about the atoms, that is, if we completed quantum mechanics, if we could find hidden variables that could demarcate for us what was different about the atoms that decayed versus those that didn't, then we'd be able to turn quantum mechanics into a deterministic theory. And a lot of work was done in the 20th century to explore the possibility of this, and the consensus was that the answer is no. You're not going to be able to account for all of the data that supports quantum mechanics by having hidden variable theory. So regretfully, physicists don't really particularly like indeterministic theories, but regretfully, quantum mechanics is one such theory. Okay, but GR, general relativity, is supposed to be this paradigm example of a deterministic theory. So we're going to turn our attention to that, and we're going to explore the indeterminism that was that is the kind of central tenet of claim of that whole argument paper by John Inman and John Norton. So briefly, when we turn to GR, we have a fundamental equation, Einstein's equation, which tells you about how the distribution of matter and the curvature of space-time are connected. And when you solve that equation, you generate models of space-time, right? So there are lots of different solutions to Einstein's equations. You can find empty space solutions that don't have matter. You can find solutions that do have matter, but any given distribution of matter will generate several solutions. So a solution to Einstein's equation is a mathematical description of a space-time with a particular geometry, a particular set of distance relations distributed over that space-time, and a particular distribution of matter over that space-time. And mathematically, these are represented as these mathematical objects that I described there in the brackets. So M is a set of points that has a particular mathematical structure, and GAB is a tensor, a metric tensor describing the curvature of space-time. So M is a manifold, that's what it's called, it's an item in topology, and GAB is a metric tensor. And so that's your basic object that's supposed to represent space-time that you get by solving Einstein's equation. But as I said, you can generate more than one solution, or more than one model, when you solve Einstein's equation. So given one solution to Einstein's equation MGAB, you can generate another solution by taking a particular kind of mapping, a function that maps the manifold to itself. And it has to be a diffeomorphism, so it has to be smooth and infinitely differentiable. But it doesn't really matter for our purposes what that looks like for the purposes of the argument that we need to address here. But you generate another model. So let me say a little bit about what these models represent, right? So the manifold has some pattern of geometry, distance relations distributed over it. When you apply this diffeomorphism and generate a new model, what you've done is you've reorganized that geometry across that set of points on the manifold, right? And then for the whole argument, it turns out you can do this with particularly interesting maps. They're maps that keep some parts the same, right? But just redistribute the geometric properties outside of that part across the two models. And so this is, there's a picture I'll show you on the next slide, right? So the idea is that you've got, on the left, you've got MGAB. It's a solution to Einstein's equation. It describes the curvature of space-time, the curvature distributed across the set of points. Time is going up from bottom to top. And then there's this region R that is that where the MD star GAB has sort of changed the distribution of the geometric field across that particular region R, but everywhere else before and afterwards is identical to MGAB. So MGAB and MD star GAB differ only in this region R, and the region R is called the whole, right? And so what do we say about these two models? They are different. They're different mathematical objects, and they're different distributions. It appears that they're different distributions of geometric properties across space-time, and if we had matter too, we'd pull the matter along with the diffeomorphism, and we'd have matter distributed differently across R2. So as models, the matter and geometry is distributed differently across space-time in this region R. So then the question is, well, do they represent the same space-time, or do they represent different space-times? I mean, it seems very natural to suppose that they represent different space-times. You might ask yourself, well, if I lived in one of these space-times, would I be able to tell which of these two space-times I lived in? And the answer is no. Any experiments that you did in one, you wouldn't be able to tell from your results of your experiments whether you were living in one of these over another. So it's an unobservable for people within a space-time difference, or objects within a space-time difference. But nevertheless, it seems to be a difference, because you seem to have matter and geometry distributed differently over the same set of points. Okay, so why does this generate indeterminism? Well, your theory is telling you that the world could be the same up to time t1, right? So in MGAB and MD star GAB, those two are identical up to time t1. But then at time t1, they're different. So it seems that there are two different futures compatible with time t0, right? And that's exactly the kind of thing that is indeterminism, right? Okay, so all well and good. All right, so in this paper in 1994, what I did was explain that under fairly controversial, but I tried to argue they were reasonable, ways of thinking about space and time, and how we think about objects across different possibilities, that MGAB and MD star GAB represent the same world. Controversial because it went against a long tradition going back to the 1600s of how we think about space-time as a thing. Influential because it's compatible, it got you what you wanted, right? It got the physicists what they wanted, because they don't want GR to be an indeterministic theory. They don't think it makes sense to talk about GR being an indeterministic theory. And I think that's partly why it was so, it's when you have a philosophical argument that, or any argument actually, that sort of has a conclusion that you like, that you think is the right one, sometimes I think you think that the argument is the right argument too, but that's not really, that you always have to be careful of that. And it became kind of the received view, and it got this title, sophisticated substantialism. But it's not quite right, because sometimes we do want to distinguish possibilities that are qualitatively indiscernible, right? That is, we do want to distinguish possibilities that are where experiments would not be able to tell you which one you were in, right? All the properties that you could observe would be the same, but we want to say they're different. And sometimes we do want to recognize that these kinds of differences are violations of determinism, right? So I'm going to now to gummy bears. Well, not quite to gummy bears. Right, so here's an example due to Mark Wilson in 1993 of the kind of situation in which we want to say that we have a violation of determinism, even though you would never know which of these worlds you were in. No amount of experimental data could tell you which of these worlds you're in, but we want to say that there's indeterminism. And we're supposed to imagine a spherically symmetric world with a tower that's perfectly spherically symmetric, that has this ball on top of it, and after a time the tower buckles from the weight of this ball, and it could buckle in any direction, right? So I've just illustrated two. It could buckle to the left, or it could buckle to the right, and the time of the buckling, let's say, is determined, but the direction of the buckling isn't determined. So Mark Wilson wants to say, look, here's a case where if you were in one of those worlds over another, you'd not be able to tell which one you were in, but still there's a difference here. There are different possible futures because the place, the points of space that are occupied by the outside of the buckle, for example, of the tower, where it breaks, are different across the different worlds, irrespective of whether any experimental setup could tell you which of those worlds you were in. And now for the gummy bears, right? Imagine me and my twin sitting in these worlds. There's gummy bears stuck to the tower all the way around. She's my identical twin, and when it buckles, a gummy bear got sprung off and gets eaten. So is it going to be me that gets the gummy bear, or is it going to be my twin that gets the gummy bear? There's a difference there. If you're in that world, one of you gets a gummy bear and not the other. And, if I were in that world, I know I'd want it to be me because I like gummy bears, right? So these are different worlds, different possible futures, right? Different possibilities for the future. And we want to say that this is a violation of determinism. Okay. All right. So already we've got attention, right? So we know that we would like to say that the worlds of the whole argument are not violations of determinism, not different future possibilities. But now we have a situation in which you also have tremendous symmetry and symmetry breaking, right? Where you want to say that it is a violation of determinism. So the original paper that I wrote in 1994, which said what we should do is we should understand that these two models of general relativity that appear identical in all qualitative ways, that no experiment could distinguish, we should recognize that they are actually representing the same space-time. If you applied that reasoning here, you'd be saying that, these two different future possibilities are the same as well. But of course, that doesn't seem to be the right thing to say here, because, in one of them it's me that gets the gummy bear, and in the other it's my twin that gets the gummy bear. So we already have a symmetry breaking violation of determinism that doesn't seem to fit with the kind of position that I was trying to argue for in 1994. And I was aware of it. I mean, I didn't, the Mark Wilson paper was written after that paper, but I was well aware that sometimes you would want to distinguish cases of futures that were, no experiment could tell you which of them you were in, but there were cases where you would want to distinguish them and say that there was a violation of determinism. Okay, so so this is a symmetry breaking violation of determinism. So there, in that 1995 paper by Gordon Bellot, he gives us an extraordinarily strange violation of determinism and asks us, okay, is this a violation of determinism? So this is what I describe as a Selkouth violation of determinism. And if you ever want to know why I use that word, you can come talk to me about it. I won't put that in print or on video under the URC. Not that it's rude or anything, but I have my reasons. Okay, so we're supposed to imagine a particle, a kind of world. It's a toy world, a particle, we'll call it an A particle that exists in space-time, and we don't have to worry about general relativity. And you don't right now have to worry about what full Newtonian space-time means. After 13 years, A particles decay into different kinds of particles, continuum many B particles, forming a spherical shell around the place of the decay. Each B particle moves at the same rate along its radius. Focus on two of the B particles, B1 and B2. B1 could have had B2's trajectory and vice versa. Nothing in the history would determine which B particle plays which role. And so here, what we have here is the kind of that spherical, the continuum of many B particles that are moving outwards from the center after a decay of an A particle at the center, and there are continuum many of them, so it's sort of just like fanning out, and what Balot says is, B1 could have played the role, could have had the trajectory, could have been over there where B2 is, and B2 could have been over there where B1 is, right? And of course, like, that's surely not indeterminism. I mean, that just seems like there's no, like, the world prior to the decay is totally symmetric. The world after the decay is totally symmetric, right? So, but on the 1994 paper example, while I didn't want to say that this kind of thing was indeterministic, there was still this problem of, okay, we've got the whole argument worlds, we've got the tower collapse worlds, and then we have these crazy worlds too. We need to figure out how it is that one could defensively say the whole argument worlds are deterministic. That's what all the physicists say. The tower collapse worlds are indeterministic. That's what physicists would want to say about that world. But this one is not indeterministic and is deterministic. And that's the basic challenge. And it's the challenge to anyone who wants to give a defense of a view where, the models, the whole argument models, the two models that are diffeomorphically related of general relativity represent the same world. Okay, so I'm gonna go through this, right? So, and the sort of the crux of the matter is, and so to this day, many philosophers have tried to answer this question of when is it that your theory is telling you that there are two possible futures, and when is it that your theory is saying that there's one possible future, and how can we come up with answers to those questions that seem to categorize the theories and the examples in the right way? And I'm sort of brushing over what this might, how this might work. I mean, there's been a lot of work on trying to do this, and none of it really seems to work, right? And which is why I have this title for this slide, what those views, and some of them are ones that I've defended, or I've sort of toyed with, are ask us to rethink the ontology of space-time theories, ask us to rethink the metaphysical approach to objecthood, and ask us to rethink whether determinism itself should be defined in terms of possibilities, right? So what seemed like a sort of good and solution to this problem in 1994 while I still think that basically it's the right solution, finding a well-motivated way that answers this fundamental question about when purportedly different possible futures are the same and when they're different, with defensible reasons, still hasn't been done. So I think that's that, and so my most recent paper on this is that. So I think that's all I want to say. I'm happy to talk to any of you. I think that it's been, I never really thought I would be thinking about this again after so many years, but as you can see, I did publish a paper on it just a few years ago. And I kind of hope that now folks in the field will take on seriously this challenge that I outline more clearly in this paper. So thank you.